So I'm going to talk today about impacts and reverberations of expanding global maritime trade routes for the Arctic. And this is funded by the Navigating the New Arctic program at the National Science Foundation. CELSO is a co-PI on this award. And I'm not going to tell you about the entire project. It's quite complex and has a lot of different pieces to it. But I want to share with you the work that I'm involved in and try to maybe make some connections here today to this work. And I'll talk about the people at the end who are involved. So, so we're going to shift gears for a little bit and start going off the land. And we're going to take this to a global level because I feel like this was where I started thinking about this idea for this pretty major project came from work I was doing at the Port of Singapore, which may sound like it's not relevant here, but I was thinking that as I was working with them, that they have 85% or more of their countries, their port operations are transshipment, meaning things come in and out, but they're not destined there and they don't come from there. And so they made a whole country, they developed a whole economy out of that. And what happens if the Arctic passageways are really open for the rest of the globe? And you know, the flow of goods and trade actually shifts in this direction. So it has not only ramifications here, but it has ramifications globally. So global maritime shipping provides the backbone for worldwide logistic operations for global seaborne trade. We saw the shipments coming in today. I thought that was really amazing to be here for that. So we know with global warming, it's inducing the decline in Arctic sea ice, and it's now going to be easier for ice class vessels to navigate the waters for greater portions of the year, and in some point, maybe even non-ice class vessels to come through. The interest in this is due to the short routes for many of the origin destinations of our trade that goes on around the globe. And these are the three routes that everyone talks about. You're probably all very familiar with this, so I don't want to go into the details of that. But you can see from a shipping perspective, the one that goes right down that center, that's the one everybody wants, right? All right, so overall, the project has many pieces to it. We have a group doing sea ice projections with high resolution, and I'll show you why we need that. Way into the future. This is not like tomorrow. This is 2070, that kind of thinking. We have community monitoring and risk assessment. That's Anne Garland, who many of you know, who's here in town. I'm doing the maritime risk and flows, and then we have an expert in conflict analysis and resolution. We think about the conflict that this could cause, and you all living here will be at the front of that. I'll just name it coastal hazards, and that's CELSO, is the back here. That's his area. So our team seeks to estimate these changes and understand how they will affect the global and regional natural and social systems. A lot of things I can skip here with you all. So you know that these are shorter, but they'll remain risky into the future. The risk comes from directions, and you all know the risks more than I can share with you. So I'll just move on. But there are also added dangers as the ice is thawing. You see all kinds of other risks for the shipping, for the vessels themselves. There's also extra costs for this vessel. So when you think about trade-offs between this and taking the Suez Canal instead, there's going to be different kinds of risks. So for example, in other areas, as climate is changing, there's also bigger storms, bigger event kind of storms that could affect them over there. And they all have risks of piracy that you might not have in this area. And so there's trade-offs that they'll have to make in making these decisions about where to route. And the extra costs also come now from things like the insurance premiums, having specialized equipment, specialized crews. What happens when there's an emergency? How do you get repairs done? Things like this. And there's risks of vessel collision and all kinds of things to the ship. So in estimating how much flow is going to shift in this direction, there's a lot of things that we can do with that information. And these are just some examples of them. We can try to better understand what the environmental implications will be. What do we need to do to protect the marine life and ways of life here? There's economic analyses that we can do, because one of the things I was saying from the beginning is if we start having more shipping here. We're going to need more people who can do things here. We're going to have ports that are going to get bigger. They're going to people who are going to have to work there. They're going to have to live there. They're going to need more things, and things will grow, and you'll have industrialization. And there's also international interest in this area from countries that can build big. So I'll just point that out. And there's local and coastal community impacts, which of course you are here at the forefront of. There's global effects. There's a need for capital investment planning. So if you really want to look ahead, building any of these ships is a big deal. It takes a lot of time. So you really want to be able to project these things. There's strategic business reasons. There's security and conflict potential. And one of the things I like thinking about, and we were going to try to work on, is could we estimate the environmental impact and try to charge for using the Arctic Passageway in accordance with that? So could we show the value and monetize it and actually show this and try to use that to help make cases for this kind of protection? Okay, so the idea is to forecast the cargo vessel traffic through the Arctic passageways under future climate predictions. And what I'm going to show you is a global maritime network that we've built, and a scenario-based mixed integer linear program and an algorithm for solving it, and explain what that does. Like, what does that mean to do that? And the idea is that we start with a generalized cost function that's based on shipping costs and times. It has root operational costs like fuel consumption, which is dependent on speed and distance. And the speed is even dependent on the risks, because you have to slow down your sailing speed to deal with risky situations. There's port handling times, there's delay, which here may not sound like a big deal, but when things get congested, that becomes a very big deal. There's delay penalties, there's insurance, cruise maintenance, and so on. So we build those into a cost, kind of generalized cost function. And we also need to assess the risks. So when you're, to be able to say how much flow we're going to get toward this direction, we really need to trade off different aspects of the different routes, and risk is big here. And so we have to be able to quantify that risk. And adding risk is very complicated mathematically. You can't just add up and say this risk plus this risk plus this risk kind of thing. So I decided to go with a risk exposure approach. Like, the longer you're out there, the more exposed you are to the risk. And the risks are different in different locations and depends on the different conditions that you're operating under. Couple other things on this. So if the risk gets too big on a route, you're not going to take that route. You can say this is just way too extreme, I'm not doing, so that you won't have that shift. And then there's polar codes that impose regulations that are also embedded within our models. So just what the model looks like, we have these different legs and ports and service routes. The service routes are like, for example, Maersk has a service route, and we pull all that data, everything about the global network, to build the global network model. And it looks like this as a topological representation of a network. And we have decision variables, and those are ultimately to try to get the number of vessels, which have two different sizes that we put in here. And they have TEUs. TEUs is the quantity for each container. So we call it a TEU. And so we count the number of TEUs that are going to flow along the different routes. So this is what it looks like to start creating some of the mathematics of it. So you have port handling times and the things that it incorporates, and some of the randomness that is associated with these things gets built in. And here, this is just an example here. If you look at operational costs in the second little box, you'll see it's composed of vessel-related costs and route-related costs, and we have to pull them into the model. When you do all these pieces and you put it all together, you have something that looks like this, and you'll see in there these little squiggles. So that is almost everywhere in the model, and that's the scenario. And it's for season M. So we're looking at it seasonally, and the length of the season matters. As the seasons get longer, there's more interest in setting up shop to be able to do this. So we then have a lot of trouble with the mathematics in terms of getting that risk exposure in there. So this is to do with that. We have to look at the risk on the different legs, and then we have to build that into the routes. And then we end up with this representation of the risk that we then pull in. Whoops, So one of the things we did a little earlier on in this project was we developed a global network model of the whole world of the top 100 bulk and the top 100 container shipping ports. And we pulled all the data from that one by hand. There was nothing like this out there. Before this, I was using a network of 6 nodes to represent the entire world. That's what was out there. So now we have a really serious updatable network that we put out for the public that you can gather the data from all the different routes that are real. We pulled them all in, and we ended up being able to show a fit of 91% to the actual annual port throughputs so that we could show that our model could represent what's going on in the world. So we take part of that network I'm going to show you in a second. So what are the risks that we're looking at? We're interested in grounding, collisions, foundering, and equipment failure. And how to, oops, sorry, I have the wrong thing. 1 second. So we developed a separate mathematical model for predicting the risks. So this is where on the right-hand top, you'll see that we divide the Arctic region into the ocean into certain sub-regions. And we need our estimates for the ice and the conditions in the water and the bathymetries and all that by these sub-regions. If we don't have it at this scale, everything looks the same. You're not going to understand like which routes are better, which are going to be more attractive. We then have a series of models the group is developing, and Celso is involved in some of this to estimate the sea ice at a high resolution, and that would allow that into the future. And you can talk to Celso about the waves part. That's my area. And we have bathymetry, air temperature, wind speed, things like this. And then I pull that, my student really pulls that into this Bayesian, is a data-driven Bayesian network approach with expert knowledge method that then computes these different probabilities, and then we make estimates about risk from that. So we build that into the model. For those of you who are familiar with Bayesian networks, I just mentioned we use a score and search-based K2 algorithm.
3 minutes.
Okay, and so now we have the data from the Arctic, from the Compendium of Arctic Ship Accidents. We get that. We build this into a kind of an exact technique. It's called Bender's decomposition, and it's very big, very, very big. So we have to run it on our, like, the supercomputers we have, not supercomputers, that's an old word, but the big clusters and whatever that we have at our university, and we still couldn't get answers in days. So we built in some acceleration techniques that then we were able to actually run this. We ran it for the 2M Alliance, which is the world's largest alliance. We have some of the details of it. When we think about risk exposure, we convert the value, which is the monetary value of losing a fully loaded 8,000 TEU container ship, about $20 million. We came up with estimates. Now, to do this, we did not have all the results from the other climate models. We now have them, but we're about to make the runs. So these were based on these 6 scenarios. So it's not using the scenarios that we're about to work with that are the true estimates. But these were designed with one of our partners on our, who is Ralph Punt, who is a captain and has navigated the Arctic and knows like everything. He teaches how to navigate the Arctic. So he helped us develop this set of scenarios, and we ran it. And one of the interesting things I'll show you, not the true data, although we have a lot of the true data in here, and we have to do the reruns. You'll see where, first of all, you'll see that how much flow is coming, under what conditions. So this is open sea ice in 5, and that's where you start to see the real shift to the different routes. And you see also who's losing, and I thought it was really interesting that Singapore, we were finding that they were losing about 20%. So it is not the real data yet. We're about to make those runs, so I don't want to look at that too closely, but we'll be putting that out. So increased cargo vessel traffic in the Arctic will affect many things that you all know about. And I ask, and this is what our project is larger in the bigger picture is about, is what are the reverberations for this changing global landscape for the Arctic region and its people? And so just to close with, this involves a lot of people. This part of it is the work that I'm doing with my graduate student, Wenji Lee, who's finished. And then we also have team members working coastal and ice dynamics. This also is in that area. We have Tom Ravens from University of Alaska at Anchorage. Jinlin Zhang is an ice physicist from University of Washington. And I think almost everyone here probably knows her. She's in the community and loves to be here. And she's been giving us real knowledge and connections throughout the first 4 years. And then Sarah Cobb is the governance and conflict resolution. And she's working on things like how to develop an Arctic warning system for conflict. So like, how do you know conflict is coming from rhetoric? So you start hearing things or reading things, and how do we know that conflict might be coming? And thank you so much.